Did you have a question? No. Okay. GHCRE?
Yes, ma'am. Hello.
Did you have? Yeah. Did you have a question?
No, ma'am.
Okay. Because you had the hand raise option selected. So, all right. So we start the class. RVIT, did you have a question?
Yes, ma'am. Hello. Good morning, ma'am.
Yes. Good morning.
Actually, ma'am, your video is not coming here. Some technical problems.
So you need
That's
to
why
set
I'm
it
unable
all
to
right
see
at
you.
where you are. Yeah. I mean, we can't do anything from here. You got to set your video correct in your side.
Okay, ma'am. I will try.
Yeah.
Thank you.
Yeah. Thank you. Okay. So we start today. So in the last class, we try to motivate you on why would you want to do electromagnetics. So assuming that you are motivated enough, we go ahead and start some basic topics in electromagnetics. The first topic that we are talking about, which according to the content that we distributed, is on transmission lines. Would you be able to beam a classroom to me? Yeah. I want to select any one college, okay. Where the video and audio is better, you can. Okay. So I'm just trying to put one class. Can you, Amrita, can you please mute your speaker? Let's go with Amrita only. Hello? Yeah. So should I be selecting this? Amrita, can you please mute your speaker? Mute your mic. Can you please mute your mic?
Yes, sir. It's already mute, ma'am.
If your mic is mute, then I should be able to hear you. If I can hear you.
Am I audible, ma'am?
Okay, we'll try. I just want one class to be in front of before I start teaching. There's no class. Yeah. What is this? TM. Okay. Which place is this? Say that again. TKM. Okay. So you'll be. So I have TKM college in front of me, so I'm looking at you and teaching. Okay. So we started the other day by saying why electromagnetics is important. We looked at the IEEE logo and we looked at the different places where electromagnetics is getting used in a day-to-day life, from the telephone lines to microwave oven to a machine to a fan to a satellite to your cell phone. So we said it's not a bad idea to do something deeper to understand the basics of electromagnetics. And the way we wanted to go around is to start from some concepts which are known to you before. So we start because I'm sure that all of you have gone through the concepts in circuit theory. You understand what is resistance, inductance, conductance and capacitance. So from that we would like to go ahead and try to see why the concept of waves electromagnetics is important. Is there a problem? Okay. So let's start with this simple problem. I have an AC source and that is connected to a resistance, load resistance RL. This is a sinusoidal source. So my voltage is a function of time, and let us say it's a single tone, which means your voltage can be described as cos omega t, where omega is the frequency in angular frequency, which is 2 pi f. F is the frequency in hertz. V naught is the peak voltage. So this is the voltage that is applied at the source. We are asking ourselves this following question. Let us say I measure this voltage as A prime across this points A prime. Okay, I'm assuming you're able to see the screen on which that I'm writing. Alright, so we are asking ourselves this question. What is this voltage? Let's say I put a multimeter or an oscilloscope to measure the voltage across that point, and the voltage across these points, which I call as BB prime, and the voltage I call as VBB prime. I know, let's say this voltage at A prime is also a function of time, and because it is very close, this is across the source, this is cos omega t. The question we are asking ourselves is, what is VBB prime at the instant t, at the same instant t? Now if you remember your circuit theory, you always assumed that this line is a short, which means the VAA, so the circuit theory assumes that VAA prime and VBB prime are identical. You would not consider the effect of this line, assuming this is a ideal, ideal electrical wire that is connecting, it has zero resistance. So you wouldn't have a difference in potential when you measure VAA prime and VBB prime. But you know, if I is the current as a function of time, the current is flowing through this wire, and let us say C is the speed, then strictly speaking VBB prime is appearing at a distance say L after VAA prime. So I should have VBB prime equal to VAA prime, the value of VAA prime at a time L by C before this T. L by C is the time taken, distance by speed is the time taken for propagating through a distance L. So at the instant of time when I am measuring the voltage at VB prime, the value that I am measuring is the value at AA prime at a time L by C before that instant happened, because the current is reaching only at a later time and the time delay is L by C. So let us say we do this calculation. So VAA prime, we already said that it is V naught cos omega t. So this is V naught cos t minus L by C, which is V naught cos omega t minus omega L by C. So all what I am saying is the voltage that I measure at VB prime is the voltage at AA prime at an instant of time L by C seconds before the time, essentially accounting for the time delay for the wave to travel from AA prime to BB prime points. Now let us try and see to calculate this number, to see how big this number is, to see if there is a voltage difference between VAA prime, VB prime, whether our circuit theory, whatever we assumed all these days, is correct or not. So let us take an example. Let us say frequency is 1 kilohertz. I want you to do a small calculation, typical length, let us say, or when we make our circuits, the length of the wires, let us say, is 5 centimeter. What would be omega L by C? Can you calculate? This would be 2 pi f length by C. So I could go back and substitute this here, and let's, to avoid complications, let's say t is 0. I am looking at an instant t equal to 0. So VBB prime at t equal to 0, I would have VAA prime as equal to V naught, because at t equal to 0 cos omega t is 1, and VBB prime is V naught cos minus omega L by C, because your omega t is 0, which is V naught cos 2 pi into 10 power 3 into length, which is 5 centimeter. So pi into 10 power 2 minus 2 in meters by assuming C is 3 into 10 power 8 meter per second, you have this number. We do a quick order of magnitude calculation. This would be something like 10, so 10 power 4, 5 times 10 power 4 over 3 into 10 power 8. So well, this is 5 into 2, 10 times 10 power, so there is a minus 2 here, so this would be 10 power 2 by 3 into 10 power 8. Let's say this is giving me almost an order of magnitude of 1. So I get approximately cos of 10 power minus 6. Alright. And if I do a high precision calculation of this number is approximately equal to 0.1234567891011 followed by 8 V naught, which we approximate as equal to V naught, even though it is not exactly equal to V naught, identically equal to V naught. But for all our approximations in circuit theory, we say, okay, this is almost equal to V naught. And we are saved by the fact that this number is 10 power minus 6. And this number is 10 power minus 6 because your speed is large and your length is small and your frequency is small. So let's write that again. Small length, small frequency, small speed. Well, not small speed, large speed. Okay. Now the speed is, we said it's 3 into 10 power 8, but that we know that it is the speed of light in vacuum. The presence of the wave, the current propagates, it might not be C, it could be a factor, maybe even up to a factor half or less than that in the presence of the medium or in the medium. But for an order of magnitude calculation, this number, the fact that we use this number is justified. So what matters is the magnitude of this number. And if I go back and look at what that number is, the magnitude of this number is 2 pi f L by C, and let's do this small thing to avoid the speed of, if I have a wave, a traveling wave, we know that the speed is related to frequency and lambda through f, so that I can include the property of the material through this lambda. So I would rather write this as 2 pi L over lambda. And I say that if this number, these two are identical numbers, identical quantities, but I just have written in terms of lambda just to make sure that I have included the property of the material. Here I have not, it is speed of light, I could use the speed of light in vacuum. So to make sure that I have included the property of the material, I put it in terms of the wavelength. Now it so turns out that this number, so long as 2 pi f L by C or 2 pi L by lambda, it's not really equal to, this is equal to 2 pi L by lambda, is small, we can neglect the simplest sense, if I say, we can neglect the connecting wires. I can pretend that those wires don't exist, it's a short, but that's only when this number is small, because we saw when this number is small, it is almost equal to V naught at t equal to 0, but this is going to be true for all times. But the question again we want to ask ourselves is, When we say small, how small is small? Do I really want 10 power minus 6 ignore? So how small should or how close this number should be to 1 so that I can ignore the presence of that connecting wire. So as a thumb rule, we are engineers, right? So we go by thumb rules. So as a rule of thumb, we say if this number 2 pi L over lambda is much smaller than 0.01, then I can ignore the presence of the fact that there is a wire. Again, the question that you want to ask yourself is there a situation where this number becomes larger than 0.01? Would I ever have a situation where this number is larger than 0.01? Which means that I cannot, what does it mean? If that number is larger than 0.01, it simply means that this number, what the voltage at BB prime we calculated, could be something like, can I have something like 0.9 V naught, which means the voltage across A prime and the voltage across BB prime, which are two ends of the seemingly short lines, are different, which means they are no more a short now. I cannot behave, I cannot pretend that those two connection wires are doing nothing to the circuit. I should start accounting for the effect of those wires. So think about it. What should I have to have this number smaller, larger than 0.01? Either I should have L large, which means I should be talking about long lengths of transmission line. Typical example is your power cables, overhead power lines, which connects your generator to your receiver. Or should have, when can this become large? When lambda becomes small. As good as saying frequency becomes large. We took the CAD frequency as 1 kilohertz. The typical frequencies that we use in electronic circuits. Audio systems, all those use frequencies of that range. So if I have a frequency of 1 kilohertz and I am talking about lines of length 5 centimeter, I can ignore the fact that there are connection wires. But let's do another calculation. Let's do another example where my frequency is 10 gigahertz. Of clock frequencies used in high frequency circuits. 10 gigahertz is the frequency. Lambda, so where do you, let's again try to see where do you use these high frequencies. Typically you would have these high frequencies running on maybe a semiconductor board, which will connect maybe a antenna source to some parts of the circuit, or the antenna receiver to some parts of the circuit. So typically you will find it embedded on a PCB or on a semiconductor material. So if I calculate the speed there, the corresponding lambda turns out to be roughly 3 centimeter, or a frequency of 10 gigahertz in free space. A frequency of, let me repeat, the frequency of 10 gigahertz in free space would correspond to a lambda of 3 centimeter approximately in a typical semiconductor material. Now let's try to see when do we satisfy this condition. So we are trying to calculate a slightly different problem. We are going to say, okay, up to what length of the line can I ignore the effect that there is a line, right? So I'm going to put this condition. I want to know if my 2 lambda is greater than 0.01, the effect of transmission line cannot be ignored. I use the word transmission line here. What did I mean here? It is just the connecting wire. That's all what I mean at this point. The connecting wire, let me put it connecting line or connecting wire, right, at this moment. So let's calculate the length then. So this would correspond to a length 0.01 times, I already told you what is lambda, so that would correspond to E in 10 power. Okay, let's keep it in centimeter. Over 2. So this is, if I do again an order of magnitude calculation, 3 and 5 is almost cancelling out. 0.01 by 2, which is 0.005 centimeter. So this is, well, 0.05 in millimeter. What does this mean? It simply means that if I am having a source at 10 gigahertz on a PCB, and if I connect it to a resistance or some load, the resistance is simply meaning the effective impedance posed by the remaining part of the circuit. It simply means that if this length of the connecting wire is greater than 0.05 millimeter, which is 50 micrometers. If this length is larger than 50 micrometer, I better consider the effect of this wire. What would this mean? Let's say instead of 10 gigahertz, let's assume that you have a clock which is running at 10 gigahertz, right, with the predominant frequency at 10 gigahertz. It simply means that at the source end, let's say this is the clock that you are sending in. At the receiver end, it's going to come out with a large delay. Because you see, if I go back this number, this to be VBB prime is going to be drastically different from what is the value at VAA prime, because the length that I am, if the length that I am choosing is larger than 50 micrometers, which means I would have taken the best conductor, I would have taken gold to connect the source side to the receiver side. But that is not guaranteeing that the voltage at this point is identical to the voltage at this point. You have to account for the delays. Right? Now the question is, how do I account for the delays? Right? How to take care of this delay? So the bottom line is, if my frequency is very large, see, we went from 1 kilohertz to 10 gigahertz, we changed by 6 orders of magnitude. 6 orders of magnitude in frequency. The length got reduced, the allowed length got reduced to 50 micrometers. From centimeters it came down to micrometers. So when you go for larger frequencies, you can tolerate only smaller and smaller lengths. On the other hand, if your frequency is small, then you can have longer lengths up to which you need not use the effect of the connecting line. So that is where you have this concept of transmission line transmission line effects. So when you have this 2 pi L by lambda, so this is the golden rule here. If the circuit that I am making has its 2 pi L by lambda greater than 0.01, you better consider the transmission line effects, the effects of the line that connects the source to the load. You can't ignore that it is a simple short. You can't ignore by saying that it's just a short circuit which connects the two. So to repeat again, when should I consider the theory of transmission lines or consider the effects of transmission line? When this condition is satisfied, when my 2 pi L by lambda is greater than 0.01. You can write, of course, in terms of frequency also. In terms of frequency, it would be 2 pi f L by c. If these are similar quantities, if this number is 0.01 came just from a thumb rule. There's nothing to do. I mean, it's just accounting for this fact that whenever cos becomes larger than 0.01 radians, I mean, you can't ignore. You can put stringent, more stringent condition. You can put less stringent conditions depending on the situation that you are dealing. So this would mean that if my frequency is large, I would reach this situation. Even for smaller frequency, if my length is large, I would still reach the same situation. So what would matter is this F product of FL or this ratio L by lambda. If the product FL is large or if this ratio L by lambda is large, you better consider the effects of transmission line. What are the transmission line effects that we are talking about? We are talking about essentially delay. We would also talk about effects like dispersion. We would talk about attenuation in addition to delay. Dispersion is nothing but the fact that this line would start behaving differently for different frequencies. In a way, it is intuitively known because this L by lambda is for a specific frequency. And I drew a pulse here, and you know very well that a pulse is not a single frequency, it's multiple frequencies. Now the line starts behaving differently for different frequencies. Some of the frequencies, the lower frequencies, the delay is small, higher frequencies the delay is large, which means the lower frequencies would arrive first and the higher frequencies would arrive later, which means the pulse starts spreading. Pulse that was like this would start spreading at the receiver. The line could also pose an attenuation. It can reduce the voltage levels with the risk that what you send is not what you receive. Have any circuit element, all what you have is connection line. So when you go to higher and higher frequency, when you're trying to build circuits for higher frequencies, for example, in a mobile phone, right, you have a large frequency transmitter and a receiver sitting inside your mobile phone. The frequency could be in the gigahertz range. Gigahertz, we took an example of 10 gigahertz. You know very well that now if the distances, the connecting wires are of larger than 50, 100 micrometers, you can't simply ignore that I connect my receive antenna to the circuit or maybe the amplifier. The voltages, the currents, the power is not going to be identical at the source and receiver, right? So any high frequency circuit, so either mobile phones or maybe any of the RF circuits, microwaves, your microwave ovens, you know, you better consider the effect of transmission. Of course, radar, you have large frequency emitting antennas, receivers. Whenever you talk about gigahertz frequencies, you have to consider the effect of transmission. Even at low frequencies, if the distances that you are transmitting is large, for example, the audio that I'm connected with, it's a low frequency circuit. But if the distance, I'm going to take this audio cable from this video room to maybe my classroom, which is like 1 kilometer away, I can't ignore the effect of transmission. I can't say that, you know, what I give, the information that I'm giving here is not the same as what I will receive. You have to consider the effect of transmission. You can no more consider this wire as a simple connection wire. All right. The next question is, how do we model transmission lines? how do we consider the effect of delay? All what we want to talk about is, if I have a way to somehow model that there is a delay between the source and the generator, then I am done. I don't have to worry about any of the other things, right? So as a circuit designer would always ask this question: I have designed my load, I can tell you what is the Thevenin equivalent of that load. It could have multiple amplifiers, it could have different things happening on the load side, but I will give you one equivalent, Thevenin equivalent, which will act as a load resistance. Same way the source could have maybe a antenna with an amplifier, or different parts, but I can always say what is the Thevenin equivalent of my source. So a circuit theory would give you the circuit equivalent, which is a Thevenin equivalent of source or voltage source. This is my source side, and all what is there on the load side I can club, and this is my RL, right? This is known from circuit theory. You do whatever circuit design and get these numbers. What we are worried about is modeling the line that connects these two guys. So we will consider it as a two-port network with two inputs, two outputs. This is your transmission line. All right. I can draw it in a more simpler way. This is itself simple enough. So this is the line that I am talking about. And what is this line doing? This line is producing a delay. So we look from the circuit theory perspective. If I could say that this line is represented by some circuit element which introduces a delay, then I am done. So ideally, what are the circuit elements that would give a delay? You know very well that I could have an inductor which can give a delay. I could have a capacitor which can give a delay, right? So what we are going to do is to model this line as a bunch of inductors and capacitors, right? So I would divide these lines into small infinitesimal divisions in terms of length. Each of this is delta Z, and say that, if I say that L is the inductance per unit length, I would want it to be per unit length so that I can apply this theory to a transmission line of any length, right? I don't have to do this model again and again for different lines. So I say L is the inductance per unit length of the line that I am considering. C is the capacitance per unit length. I could also model the resistance, because you will realize that at higher frequencies the wires which it's a frequency dependent quantity, resistance per unit. And I could also model the resistance of the capacitance. So this could be the resistance, the resistive component of the inductance, essentially to say that this the coil could have its own resistance, and G, conductance per unit length, to model the effect that the capacitor, the plates of the capacitor are supposed to be separated by an ideal dielectric, but practical dielectrics are not really ideal. There could be some, to remind you, a dielectric is a insulator, but no dielectric is ideal. It would have some conductivity. The conductivity could be 10 power minus 8 or minus 9 or minus 10, but it's not identically 0. To account for that, you could have the conductivity. And the way you are going to model this is the proposition. I would have model it as a resistance, inductance, a capacitance, a conductance. This is equivalent to a length delta Z, right. So I would have this. What is the value of the resistance? This would be R is resistance per unit length. I have a length of delta Z, so this would be R delta Z. L is the inductance per unit length. I have a length delta Z as a length, so the total inductance will be L delta Z. Similarly, C delta Z and G delta Z. Alright. So this is modeling, this is the circuit model of a transmission line, elemental length of the transmission line delta Z. What's the good thing about the model? The good thing is I know how to deal with resistance, inductance, capacitance and conductance from my circuit theory. So I can just apply Kirchhoff's voltage law and Kirchhoff's current law and find out if I apply a voltage VZT here, what is the voltage at VZ plus delta Z at the same time. So the goal is, if I know this, how do I find this? The goal is, if I know I Z of t, how do I find I Z plus t? What we should do is simply apply KVL and KCL and get the answers for what is the current and what is the voltage. Once I know that, I just keep looking for all these infinitesimally small segments, reach the end of the wire, then I have solved my problem. I know what is the voltage here. If I know the voltage here, I can find out what is the voltage at the load. So that is the way we are going to solve this problem. So I stop at this point. I just quickly summarize what we did today. We did example where we found out that the effect of the connecting wire between a source and a load cannot be ignored when certain conditions are satisfied. So we tried to derive what those conditions were, and we figured that this factor L by C or omega L by C is what is determining whether you can ignore the effect of transmission line or not. And we figured that when the frequency is low and if you are at some reasonable lengths like 5 centimeter or 10 centimeter or even 1 meter, the voltage at the two ends are almost identical. But when we consider a frequency of 10 gigahertz, then we figured that even if your length is larger than micrometers, 5.05 or 50 micrometers, you cannot ignore the effect of the connecting wire. So that brings us to the concept of transmission line effects. And the first question, so when you are designing a circuit, an electronic circuit, the first question that you have to ask yourself is, what is my 2 pi L by lambda, or what is 2 pi F L by C? If that number is larger than 0.01, you better consider the transmission line effects. Then we went ahead and said, how do we cover the transmission line effects? There is an electromagnetic way of doing it, but let's not do that because we have not done electromagnetics yet. Let's start from what we know. We know circuit theory very well. So all what we want to model is model the delays. So to model delay, we know that inductor and capacitor are the ideal ways of modeling the delay. Now to account for non-ideality in inductance, we include the resistance. Similarly, to account for non-ideality in capacitance, we model the conductance. Then we say that you divide the transmission line to small infinitesimally small elements, and each element you represent as an inductor, capacitor, inductor and resistor in series, and a capacitor and a conductance in parallel. And tomorrow in the next class we will try to figure out how to find V and I at distance Z plus dz given what is V and I at Z. That's what we will do in the next class. So now I open the session to questions. So if you have a question, please hand raise. Okay, so BTKIT, what is your question?
Good morning, madam.
Yeah.
My question is that is suppose that we have a DC source.
I'm sorry, I can't hear you. Can you increase the?
Can you hear me?
Yeah, can you? Yeah.
Madam, if we have a DC source
Yeah.
and circuit length is small or big.
Okay, your question is if I.
If we have a
The
DC
question
source
is.
and
Yes.
if circuit length is small or large, there is any kind of effect?
Okay, the question is a question for the benefit of everyone. If I have a DC source, should I consider the effect of transmission lines? Is that your question?
Yes, sir.
Okay. Okay, the answer is if you have a DC source, you still have the effect on transmission line, but those would be at the transient level. So when you would turn the switch on, you would have the voltages just like an RC circuit. How would an RC circuit or an LC circuit or an LR circuit behave in your circuit theory? You would have transient effects and then it will settle down to a steady state value. Same is happening in a transmission line because after all your transmission line is modeled as a resistor and capacitor circuit. I mean inductor and a capacitor circuit.
Okay, thank you.
SMIT, what is your question? SMIT, what's your question? Maybe you should keep your mic turned on.
Good morning, ma'am.
Yeah, good morning.
Just now, BTKIT teacher has asked the same questions whatever I have asked. If what happens if the source is DC? So I have got the answer.
Yeah.
Thank you.
Okay. Okay, fine. JSC. Good morning. Can you repeat? Can you say that again? Yeah. Huh. Why is the L by lambda 0.05? Is that the question? Oh, 0.01. Okay, so 0.01 is thumb rule. Because if that number is 0.01, you remember earlier we calculated V0, we calculated VBB prime as so many 9s followed by 8 not. That is because that argument in the cosine was 10 power minus 6. Okay. Now if that argument becomes 10 power minus 1, you can estimate what is cos of 0.01 and then you will realize that the number of 9s would reduce. It will come out to be 0.9998. and then you can't ignore the fact that VBB prime is not V0. So that is the reason why we have that 0.01 number. Does that answer your question? All right. PSG.
Good morning, ma'am. And
Good morning.
what will happen if we replace that wire with a superconducting wire? Will the same innovation apply?
What will happen? Can you repeat your question little slowly because its voice is not clear?
What will happen if the wire is replaced with a superconducting wire?
If the wire gets replaced by a superconducting wire,
Yes, ma'am.
so even for the superconducting wire, you would want to, any superconductor also would get modeled as resistance. So what would a superconductor do? A superconductor would have very low resistance, right? So you would reduce the R, you would reduce R to a very low value. Depending on how you have your superconductor made, you could still have L and C getting included in the circuit, right? So line is can't ignore transmission
Okay, thank you.
if your frequency is high.
Thank you, ma'am.
Yeah. MLVG Tech. What's your question? MLVG Tech, what's your question?
Hello, good morning, ma'am.
Okay, let me go to the next teacher, RVIT.
Good morning, ma'am.
Good morning.
Hello. Yes, ma'am.
Yes.
I want to ask that why we are considering the effect of conductance in the transmission line.
We are considering the effect of conductance because, as I mentioned in the class, we are modeling this delay using an inductance and a capacitance. Now, an inductance need not be ideal. The non-ideality of inductance we are accounting by considering a resistance. The capacitance is not ideal. So we an ideal capacitor would have two perfectly conducting plates separated by a perfect dielectric. A perfect dielectric is a perfect insulator, right? So you would want to consider the non-ideality of the capacitance through a conductance. So ideally the conductance has to be 0.
Thank you.
Is that clear?
Yes,
I have
clear,
another
ma'am.
question coming up from VCAP which says in power systems we will neglect. So VCAP, there is a question from VCAP. I'll read out the question for everyone's benefit. In power systems we will neglect the effect of inductance and capacitance in case of short transmission line. When the line length is short, you are never reaching this condition. You are always having 2 pi L by lambda much less than 0.01. You will have your length short, for short lengths you will have this. So we neglect the effect of transmission line, which means you will neglect effect of inductance and capacitance. The other question I have is, how inductance and capacitance affects in long distance communication from MLVG Tech. So in long distance communication we can talk about wireline communication or we can talk about wireless communication. Now in wireline communication it could be copper or it could be an optical fiber cable. If it is copper, you would model it as whether you are using a twisted pair or whether you are using a coax cable, what kind of cable you use, you can exactly find what is the inductance, what is the capacitance, all these transmission line parameters, RLGC parameters, right. In a later class, I will tell you how to find parameters, for example, for a coaxial cable, right. So you can account for that. In an optical fiber, you don't call it as RLGC, but you call it effectively as a resistor. It's all the same, but you don't model it as an RLGC because it's not an electrical circuit, but you model it as a dispersion parameter and you have a standard number for that dispersion parameter, 17 picosecond per kilometer nanometer. So every kilometer would produce a dispersion or a delay of 17 picosecond. That number is known to us. Alright, so I hope that answers your question. KNMU says we are unable to see what you are writing. I hope other colleges, did other colleges, I'm connected to RVIT. RVIT, were you able to see my writing?
Yes, ma'am. We are able to see your writing.
Okay.
Yes.
Okay, fine. So that is a problem specific to KNMU. So they have to deal with how to find, how to share the screen or how to see the shared screen. Okay. JSC, what is your question? JSC, what's your question?
Good morning, ma'am. When you explained that what happens when we apply a DC signal, actually the answer was not clear to me. Can you please repeat? Explain it again.
Can you repeat your question?
What happens in the circuit when we apply a DC signal?
What happens when you apply a DC signal?
The previous explanation was not clear to me.
So, can you see the shared screen? Can you see the whiteboard?
Yes, ma'am.
Okay. So, if I use DC, this is what will happen. Think about this transmission line. I apply a DC voltage as a function of time. I turn my switch on at this instant and keep my voltage on. This is my DC. This is the instant of time at which I am keeping my switch on at, let's say, T1. The fact is, this rising edge would take a longer time to reach here. So what you would see at the end, at the receiver, is to the first approximation this. And there's one more big thing which I am hiding from you now, and that is there would be, you would realize later that there would be reflections happening at the voltages at the receiver if the impedances are not matched. So as a function of time, it might not be very clear to you now, but maybe in the next few lectures it will come clear. It is not really going to be this, it is actually going to be this. Which means at the receiver, it is not really, it's not just that it is delayed and it is reaching the steady state. It will reach the steady state only slowly. So this effect we will consider in detail towards maybe I think 6th lecture or something, where what happens, we will specifically discuss the case of DC. I hope that answers your question. TKM, what's your question?
Ma'am, we have now derived this condition for the resistive load. If the load is to an inductive or capacitive load, will there be any changes?
In fact, when we derive this condition, we consider any resistive load. We just said that I put a resistance there just to make sure that I have an electrical circuit complete. That's all. I don't care whether it is a resistive, what kind of load it is. All what I consider is omega L by C, where it does not depend on whether it is a resistance or a conductance or what it is. So at this moment, the load does not matter. It will of course start mattering, which we will come back later when we get into the details of transmission. But at stage for this condition, that this 2 pi L by lambda being small condition, we don't care what the load is. Does that answer your question?
Thank you, ma'am.
Okay, Amrita? What's your question?
Hello. Ma'am, in the last circuit you have drawn, the resistance and inductor are connected in series and the net one is connected with capacitor and conductance in parallel. So why is the circuit like that actually? Why can't we connect in any other way?
If I connect capacitors in series, I can't get this line working for DC, right?
But why do we generally, if you see for transient circuits, like when we can, generally when we see for
I want this model to work for any frequency starting from 0 frequency. So if I put my capacitance in series, what does it mean? That will start blocking. Similarly, if I put my inductor in parallel, then also I have a problem. This is a very generic model. It allows for all. But at this, you would find techniques which would have here, inductance here, and then in the middle you have capacitance, and then you have conductance. Or you could do it something like resistance here, you could have capacitance here, conductance here, R, L, so long as all these are allowed, so long as your inductance in series and the capacitance in parallel, you can distribute the way you want.
and I
You want
have
your capacitance in parallel and the inductance.
Yes, ma'am. Why do we include the factor of conductance? Like generally we use resistance and inductor and capacitors for time delay. Why do we include the factor for conductance also, which is not used in DC transient circuits?
Is there any other question from Amrita? Okay, so the time is up, so we'll see you next Tuesday. Right. So the laptop done or can you just leave it at my office? Ask somebody, they know my office. Okay. Or in the telephone. Okay.